So yeah, thanks for everybody for joining. Also, a big Caribou Sana to Jessie, who's joined us from Kenya this evening as well. Hi, Jessie. Yeah, so I'm going to present to you some of my PhD work. It is just a snippet of what I've been doing, but I've really enjoyed it, and it's at a point where I'm sort of happy sharing sort of thoughts and sort of definitely open to some feedback at the end to help me sort of process some of my ideas. So it's exploring aspects of the structural controls on Caldera hosted geothermal resources. And this is a photograph of Menengah Caldera, my field area in Kenya, photograph taken from the eastern rim, looking sort of not quite west, sort of west-southwest approximately. Yeah, so we shall move on. And of course, my laptop has decided to play up. There we go. Okay, so I wasn't entirely sure what people's backgrounds were with regards to calderas as such. So I thought I would just quickly go over some sort of key aspects of calderas. So sort of nice sort of schematics, easy to follow sort of diagrams here for you. And you'll see that the topographic diameter and structural diameter are quite often very, very different. So just little aspects. First of all, structural caldera floor, of course, that's the subsided pre-caldera land surface. Your ring faults, they tend to be subvertical to vertical. They're sort of quite often bell-shaped, so the top of them curves inwards. So you can just see those here. And almost always they are buried by post-collapse activity. Peripheral fractures and satellite ring faults are key for development of the topographic rim. So you get radial and concentric fractures. They form above the bell fault, so you could actually sort of imagine it's extending out to some degree and sort of forming along here. Hope everyone can see my blue cursor there. And they result in scarp retreat, formation of the collapsed collar, and a topographic rim. And so you sort of this kind of thing happens, and then your collapsed collar forming there. So your collapsed collar is essentially the rock between the topographic caldera ring and the ring fault itself, and usually that's actually a void because it's collapsed into the caldera, as mentioned before. And then the collapsed slope is basically the sort of the average angle from the rim of the topographic rim, and where the ring fault actually is. And of course, if you're trying to ascertain what this angle is after collapse and refill, you quite often have to make some assumptions. Usually you're looking at the slope itself, so that dashed line is usually between sort of 25 and 45 degrees from horizontal. And then your topographic rim itself, bounding escarpment with steep to over-steepened slopes, scalloped where collapse has been irregular. And of course, your post-caldera fill and breccia. So this is where you've got your collapsed debris from your over-steepened ring faults, and obviously resurgent activity, volcanic activity after the initial collapse. And then mechanisms. So there's 5 end member mechanisms. Generally speaking, calderas are dominated by one of, but they're very rarely entirely one of. There's usually an aspect of something else involved. So you first of all got your plate or your piston collapse. So the entire floor, generally speaking, drops in one go. They do create massive eruptions, and the magma chamber is very shallow. I should say as well here that the nature of the collapse, the mechanism, is actually quite often associated with the geometry of the magma body and in the subsurface as well. And you tend to find that the calderas are greater than 10 kilometers in diameter, and an example is the Silverton one in Colorado. So you've got at the top there a cross-section, a very simple one, and at the bottom is sort of schematic plan view, where the outer ellipse is your topographic rim, and then your two inside ones. So that red area is the proposed area of your ring fault. And these ones tend to have activity after the collapse along the ring fault area, and very rarely sort of towards the centre, because the damage to the floor is limited to negligible. Piecemeal chaotic collapses, hence disruption to the floor, really chaotic, very complex fracture networks associated with this collapse. And you quite often find multiple nested or overlapping collapses. Activity on the caldera floor afterwards is quite often randomly distributed. So you'll have fumaroles, geysers, volcanic eruption centres randomly distributed across the floor, and that's because the chaotic fractures associated with the collapse are feeding these eruption centres. And an example is Campi Flegrei in Italy. So trapdoor mechanisms is an intermediate between the plate that I mentioned first and the downsag that's also on this slide. You have a partial ring fault that's hinged on the opposite side, and it's an asymmetric magma body. An example of that is Snowdon in Wales, and you can see there in the plan view on the right hand side, the sort of the darker images are sort of concentric fractures that are associated with the hinging effect as well. And then your downsag, volcanic deflation is common, not just in caldera systems, but generalized volcanic systems anyway. It's an indication of sort of very subtle drainage. It can also occur when there's a drop in water recharging the subsurface. So you'll see certainly at Yellowstone, you get slight seasonal changes in inflation and deflation that's nothing to do with magma movement, but to do with snow melt. Most calderas are thought to start in this way and then progress. There's no ring faults, and they're just replaced by concentric fractures. Doesn't generally affect normal activity of the volcanic centre, and you don't tend to see a great deal of activity at the surface. And you have an example there of Sakugi in Japan. And then the final one is the funnel collapse, common in Japan and the Northwest Pacific Ring, characterised by upward flaring of the primary eruption conduit. They tend to be really, really small, so sort of 2 to 4 kilometres with a really deep magma chamber. And probably a familiar example of that is the Nova Rupta event at Katmai. Excuse me. I'm not going to spend too long on location, but you've got a DEM on the left of the rift system, East African rift system. I'll put that on there just simply because I really like it. But the Google image on the right, so you've got the eastern branch, the western branch, and the southern branch. You'll also notice continuing sort of towards the southwest from the eastern branch, if you can see my blue cursor there, you've got hints of rifts coming in here as well. And some of them are active, some of them are subdued, but the main border faults are believed to be inactive now, and accommodation is occurring within the rift due to brittle faulting and dike intrusion. And it's worth saying here that the border faults are listric, so they're sort of shallow, dipping at depth to almost flattening out as well. So continuing with the location. So this is sort of DEM of Kenya in both images there. And these red dashed lines are the approximate location of the Aswar lineament. And the Aswar lineament is a very large myelinite zone that extends from Sudan down to the Mozambique coast. And it's thought to have been a transform fault associated with Pan-African collision. And the rift and extension has been largely reactivated along many of those Pan-African structures. The black dashed circle is the rough extent of the Kenya Dome, and the blue dashed lines are the Central African Rift System, which was one of 5 branches that extended out from the Cameroon region during the later breakup of Pangaea, and this rift ended up as a failed rift. And then the DEM on the right is just showing you the location of all the volcanic centres. In Kenya, blue triangles are large-scale intrusions. Across Kenya, there is approximately 147 eruption centres, but all in yellow are believed to be extinct, and the ones in red are currently the active systems. And if you can see my blue cursor, you've got Menengah is just that red one there. So not only is it sitting within this sort of myelinitic zone as well, that also controls this change in the trend of the rift, it's also very, very close to the Gregory Rift, Kivaronda Rift triple junction as well. So it's a really complex area, structurally speaking. Just thought I'd throw this in very, very quickly. So the sort of more up-to-date interpretation of geothermal plays and East African Rift Valley, despite it being volcanically active, is actually dominated by extensional. So it's an extensional play on a regional scale, and then on a local scale, you've got volcanic. So it's actually determined or classed as a hybrid play system. So introducing Menengah, what can I say apart from the fact that I love the place? Top image again, there's that one from the start, and on the left you've got Lion Hill, highest point of the Caldera rim. You can just make out, if you follow my cursor there, I'm hoping everyone can see it, that's the extent of the caldera. And this is probably the youngest flow, looking at cross-cutting relations, and it's an obsidian rhyolite flow. And then you've got this photo at the bottom here, again, is of the caldera. This is the obsidian flow just here. And this photo is actually taken from the top of Lion Hill. So you've got sort of roadworks, and you can see some sort of well paths are cropping up. And this area here is one of the fumaroles. There's a lot of altered ground here. So it's a broad trachyte shield, about 180,000 years old, elevation of 7,474 feet above sea level, 2 collapses, 35,000 and 16,000 years ago. The first collapse date is much more recent. It was initially thought to have been 29, but it's been redated. The pyroclastic density currents from the collapses covered a total area of just under 1,300 square kilometres. Ash was also found in Lake Victoria, which I believe is about 350 kilometres away, and to the east of Lake Turkana, which is way up in the north, close to the Ethiopia-Kenya border. Chemically, trachyte, phonolite, obsidian rhyolites. There's 70 post-collapse eruptions in the northeast. There's evidence of the Galilean high stand caldera lake. There's also evidence of post-collapse phreatomagmatic eruptions associated with that lake. And we can use the caldera, we can use the collapsed collar slopes to calculate where the caldera rim is. But before I go on to that, just to bring it sort of into context, Menengah is believed to have been a volcanic explosive index of 6. And that's your volume that was ejected during that. And just to put it into context, you've got data there for Mount St. Helens, Nova Rupta, the 1883 Krakatoa eruption, Vesuvius, Toba, Yellowstone, and Wawa Springs as well, just for context there. Sorry, yeah, so caldera from Google Earth, you can clearly see sort of the well-defined outline of the topographic ring. Lots of wells, you can see quite clearly there. And then the schematic on the right, so you've got the outline of the rim there. And then, as I mentioned, using the 25 degrees and 45 degree angle from the top of the topographic rim and projecting down to roughly a depth of 800 meters, you get an approximate location of the buried ring fault highlighted in this pink. But there were 2 collapses, and currently we can only really estimate where one ring fault is. Just a quick summary for the geothermal development in Menengah, for those of you who are not familiar. The surface exploration began in the late 1990s with one microseismicity survey that identified the brittle ductile transition zone beneath the caldera to be around 5 kilometres. This was continued in the early noughties by magnetotellurics and gravity surveys. And the first well, which was well 1, was completed in April 2011. And the first deviated well, 1A, shortly followed after that, and is currently Africa's most powerful well at around 35 megawatts. Although Kengen Olkaria, there are debates between Menengah and Olkaria as to who actually has the most powerful well, because they are very close and they do fluctuate slightly sometimes. 3 development phases, each will be around 105 megawatts. As of last year, they had 26 vertical wells drilled, 16 deviated, with a further 20 planned, and some of those drilled wells have failed for various reasons, continued loss of circulations, or was dry, or a whole host of things. And the high temperature reservoir is around 1900 meters below surface and sits within the epidite-illite wollastonite actinolite zone, which has a temperature range of 190 to 340, but the bottom well temperatures and the alteration minerals in Menengah indicate the upper temperatures of this range, so sort of 300, 320 degrees. So methods, I mean, I'm going to concentrate predominantly on CO2 flux and gas sampling work that I've done in Menengah, but I have also included some water data and some of the basics I've done from some play mapping within the caldera. So you can see here on the left, collecting soil gas samples. You can, from this, we're sort of assessing what the concentrations are, what the composition is, and also collecting samples for analysis of carbon-13-12 ratios as well. And this is a method that's used by, that's talked about by Hinkle and Kilburn. There is a slight update on this, this method that the British Geological Survey used, but generally speaking, it's very similar. And then we use an EGM4 environmental gas analyzer, which is the big image there on the right. These are charged by mains. They weigh about 1 kilo, so really easy to transport around the field. They're really, really compact and small. And they're also really tolerant of high temperatures, which is really, really important, because some of the ground temperatures are sort of in excess. It's sort of 75, 80 degrees Celsius at very shallow depths. I've used the Leica in the past, and it's really temperamental at temperatures over about 35 degrees. So CO2 flux results. So I've got in the top table there the range from non-detected up to 875 grams per meter square per day. It should actually read 0.24 up to 879, because that's the detection limit of the flux system, the PP system. Looking at this graph on the right-hand side, using Sinclair's stochastic modelling of chemical data, you're able to identify your background biogenic CO2, what's mixing and what's volcanic. So everything in here is sort of mixing between volcanic and the background biogenic CO2. And the volcanic, I mean, it is volcanic, it does calculate as being volcanic, but you really would want a much stronger deviation in this curve. So there's a slight change in that, but really you would want it going off here. So there is some volcanic contributions, but it's quite limited. But the baseline is 82.2 grams per meter square per day. And that can also be used if you're doing regular monitoring for volcanic unrest. And if that was to change a great deal, then there's something going on. As CO2 is, after water vapour, the fastest gas to escape from a magma chamber. And then you've just got some percentages there as well. Now, the histogram shows a significant skew. So most of it, as we've seen with the cumulative frequencies, is biogenic. But as we're getting over to the right-hand side, we're starting to get that little hint of volcanic contributions coming in. Ooh. Sorry. So despite the cumulative frequency actually stating that there's very, very little contribution from a volcanic source, the carbon-13-12 ratios suggest that there is. So Darling et al. In 1995 established that typical volcanic carbon-13 values for the Rift Valley are between -2 and -6. And you can see my data here in red. It's got a very broad coverage, and this is because I randomly selected areas to sample from right across the caldera. But you will see that I have a cluster of data that falls within the -2, -6 range. And then the other data here is from various locations across the Rift Valley, both in Kenya and in Ethiopia. And although pretty much all of that data is very much very much clustered around the typical Rift values, those surveys were also very much more targeted. So they knew where the features were, they knew where the ring fault at Longonot was, they knew where the fluid conduits at Alutu were. And so the surveys themselves were a lot more targeted than mine were, and that's why their data concentrates a lot better within that range. So the results of the CO2 flux, this is basically what it looks like. So I used empirical Bayesian kriging in ArcGIS, and you've just got a few sort of basic stats there on the left-hand side. But what you can see there is your high and your low values. And it's probably worth pointing out here that based on the CO2 flux at Menengah, the annual discharge of CO2 to the atmosphere is in the region of 4.5 to 5 tons a year. So it's actually really low for the Rift Valley as well. So there's definitely stuff going on here, but I suppose it's a question of what. So because CO2 is a rapid escape, and it's going to preferentially move along faults to the subsurface, you're going to get higher concentrations in some areas that indicate permeability zones. And so you've got sort of you could argue lots of linear features on a sort of a north-northwest, south-southeast trend, east-west trends and things like that. But then if we also bring in the fumarole locations, so they all seem to sit predominantly along that east-west line with a couple of more random ones. And then the volcanic centres, which are fairly random with the exception of the ones in the southern half of the caldera. And if you remember when we were talking about piecemeal collapse mechanisms earlier on, I was saying about how eruption centres and any surface activity can be random. And so it suggests that the caldera is most certainly a piecemeal style collapse. But there is also something quite significant going on in the centre here. And my thinking on this is that it's potentially the second ring fault. You have to remember that it's, CO2 as with water, it's very, very diffuse. So it's not going to rise to the surface along a single line. It will diffuse out along all the fractures that are associated with any faulting. But this is my thinking at the moment. It's also worth pointing out that roughly from this area, when you're traveling north across the caldera, there is a significant drop in elevation. And when you're speaking to the people that work in the caldera and the locals, the farmers that live in the caldera, they refer to the caldera as upper and lower because of this significant drop in elevation approximately in this area here. So further sort of interesting thoughts here. So this isn't all of the wells, by far this is not all of the wells, this is just some of the wells that I have some information on with respect to where the deviated wells are located. And what you'll see there is the successful wells, deviated wells, pretty much all target this feature, even though they don't necessarily realise that that's a ring fault. Also bring in there, so you've got here on the far right, you've got a black line here, so that is a deviated well, when I was at the GDC office in Nakuru, they were wondering why this well was really tight, borderline failure. And it's probably because they've missed, they've certainly missed this proposed ring fault, but also there's a graben system here, so it's the southern extent of the Salai TVA, and this fault that runs through here dips to the west, and this fault dips to the east, and so they've probably gone into that central bit and missed all the damage zone that would be essentially used as fluid conduits. And then this one here, this has failed with respect to the production of electricity, but for heat, this is where they have a direct use product, a direct use site, and they're using the heat to pasteurize milk, heat greenhouses, fish aquaculture and things like that. So it's not a complete failure by far, because obviously here in the UK we're very much familiar with that need for heat production from geothermal. And then I just want to add these two in because these are two wells that have discharged successfully. They're within the centre of the caldera, but they're not targeting the this proposed ring fault of the second collapse. But you could, of course, argue that there are other features running through there. So there's certainly at least 2, maybe even 3 linear features that might coincide with those deviated wells and the success of those as well. So enthalpy chloride mixing. So the bottom values here are the values calculated from data collected from well samples themselves. And then everything else is converted and calculated from this data to ascertain the conditions prior to rising to the surface. So these bottom values are your sort of your wellhead values, and these are your sort of calculated reservoir values. And to do this, I've used Arneson et al. 1983 silica geothermometer. So using the silica values collected, calculating the temperature, converting that to the enthalpy and plotting it. At the top here, the SP, that's your steam point. And then the dashed blue line here is your Menengah boiling line. So water boils at about 92.5 degrees at Menengah because of elevation. And then you've got your meteoric water average value in red, with the range in the black box there. And using this, we can look at mixing between wells. So we've got, first of all, what looks like boiling going on between some of the wells, but this is boiling with respect to a loss of pressure, so shallower depths, so maybe some vertical flow between these wells. You've also got, oh, excuse me a second. There we go, sorry. There we go. So the blue one there is mixing between wells with meteoric water. And then the black lines, black arrows there is again boiling, but it's boiling within the reservoir. And then we also have a couple of examples of where we've got mixing going on. And boiling because of loss of pressure, and then it's rising, then the water's rising to the surface through the well and boiling as it arrives at the surface as well. So there's a whole host of mixing processes going on here. In addition, some of the isotopes from some of the wells, I definitely would have liked more isotope data. This is data that Geothermal Development Company were very kind to donate. The red plots are the data from the wells, and the blue dashed line is the Kenyan Rift meteoric line. The KRML is consistent with evaporation of meteoric water with respect to the global meteoric water line, so it's slightly lower hydrogen, and slightly more enriched in oxygen, and that's expected in Kenya anyway because of its location geographically. The red one here towards the so enriched in oxygen but very little hydrogen, That sample there has clearly undergone boiling with respect to the Kenya line. And if we, it's obvious that all the wells are boiling to some degree or other. So if we sort of almost project back using this value here, and it would vary across wells. So this is sort of just something I was playing around with. But if we project back from all of the measured points backwards, we find that water in the reservoir is enriched in chloride, deep chloride fluids that quite often indicate mixing with saline waters. And then this, as I said, this positive shift down here is boiling and an indication of fluid rock reactions. But the mixing with salinity waters is quite interesting, and I'll touch upon that again in a moment. It's also fairly rare, comparatively speaking, to find this in isotopic data for geothermal reservoirs. So discussion, I'm racing through this. So I've put together sort of a quick cross-section, east-west cross-section through Menengah, and initially looking at the subsurface within the caldera. There's very little sort of supporting evidence for how water might be getting into the caldera. The listric faults flatten out beneath the caldera at some depth, and then of course you have your piecemeal structures, the sort of vertical or close to vertical, that water could certainly rise along. But you also have the Salai TVA and the Kayamandi fault zone as well. It's currently estimated that Lake Nakuru to the south contributes about 30% to the reservoir, and then the remaining contributions are coming from recharge on the plateaus and permeating down along the listric faults. But like I say, there is limited sort of based on the cross-section data, there's very limited evidence as to how this water is getting to the caldera. So I don't know how well that map's come out for you guys. It's actually a lot bigger, and I've just cropped it. But this is an outcrop map by McCall that he did in 1957, and I've digitized it. And then you've got the photo on the right-hand side here, looking south from the caldera rim over Lake Nakuru. So you can see Lake Nakuru in the distance there. And then this ridge on the left of the lake is Sircon Ridge, which if you look at the map is that sort of green strip there. And then you can't quite see it because of the mist, but there is a ridge here as well that extends north as well. That's the southern extent of the Kayamandi fault zone. So I'll do that. So the ridge is here, and it's not actually on this map, but the Kayamandi fault zone is through here. You've got Proctor's fault here and David's fault, and there's lots of fissures and fractures and things in this area as well, and they're associated with the Kayamandi fault zone. And so the thought is that at least this 30% from Lake Nakuru is flowing along the faults that are buried under this tertiary, under these under these recent deposits. Lake Nakuru is fairly saline, and so it could be that the saline that we're picking up, salinity that we're picking up with the change in isotopes, is associated with recharge from Lake Nakuru. But for sure, certainly more work needs to be done. More data is definitely needed. But yeah, so already concluding a nice short presentation for you all. I guess sort of my take-home things here would be to make sure you know your caldera. We've seen by the different collapse mechanisms what type of activity you might get, and piecemeal collapses are by far the best sort of structures to be targeting for geothermal development, where you're drilling within a caldera rather than drilling outside of a caldera and deviating into it. So know your caldera types, know what collapse mechanisms, know if there's been multiple collapses and what those dominant mechanisms are, or if they even differ. Make sure you have your baselines in place. So I mean, Menengah is still classed as an active volcano. And so we should know what the baselines are. So we should know what the seismicity is, the background seismicity, the background degassing, and so on and so forth. We saw for the first time the effects a volcanic eruption can have on geothermal power plant after the damage at Puna following the Hawaii eruption. But they had everything in place to mitigate against that. And so they were still able to pay their employers because they knew the activity of the volcano. And yes, Hawaii is very obvious, but it's still really important to know what's going on. In the case of Menengah, the ring fault associated with the first collapse does not appear to be influencing the overall geothermal system. It seems to be contained within that proposed second ring structure. The flux clearly identifies this zone of high permeability, and it also coincides with the fumaroles and the eruption centres and the successful wells that have been drilled so far. The water chemistry and the isotopes and the enthalpy chloride mixing, despite regardless of the processes going on, so whether that's boiling or cooling, mixing, etc., this data seems to also indicate something is going on across the centre of the caldera. These mixings between wells and boiling between wells and so on and so forth also seem to occur along that roughly east-west feature, with further circulation going on where the proposed second ring fault ends west and then north. And I can obviously go back to that if you want to have a memory refresh. So is this the second ring fault? Well, I think it probably is. Philip Leet in his PhD thesis actually had the first and the second ring faults pretty much sitting in the same location, and the first ring fault being buried by the second collapse. And he also had that the first collapse discharged the 20 cubic kilometres of debris, and the second collapse discharging the slightly larger volume. But I think the second collapse, if this is the ring fault, would have been smaller, and so the volumes would have been the opposite way around. But yeah, as for sure, as I said earlier on, for sure, more data and more work is definitely required at Menengah to identify what is certainly controlling the system. But there's definitely a story there that I think is really interesting. And that's it, really. I hope everybody enjoyed that. Nice and short for you all.
Thank you. Can you hear me okay?
What was that, Claire? Yeah, I can hear you, Claire.
Awesome. Thank you so much for taking us through that. Are there any questions by anyone?
I did see there was something in the chat, but I can't find where the chat has gone.
It's up the top right-hand side, and it's just me when
yes.
Everything cut out.
Okay, fair enough.
I have a generic one for Helen.
Okay.
You kind of touched on it a couple of times, but maybe just if you have anything else to add. The overall sort of link between caldera and structure in general in that region. I mean, so a lot of people talk. It really depends if you talk to the volcanologist or the structural geologist about that sort of chicken and egg situation. Did the rifting allow the caldera to form, or does the caldera control the structures that that facilitate fluid flow going forwards and all that kind of stuff? I mean, what kind of, are you leaning any particular way at this stage based on what you've seen?
I mean, if you were to look at the play types, because the rift system is a perfect example of a hybrid, it is a chicken and egg. It is a sort of, does magmatic convection cause rifting, or does rifting allow for buoyancy effect? But when you look at the plays, they seem to indicate that the initiation of the system is associated to rifting. There is some literature out about the structural controls of the shape of calderas. It was something that Riftfold did, so it's Juliet Biggs and Elspeth Robertson, I think her name is, did a couple of years ago. And as much as they're saying that the long axis of calderas seem to align with the principal horizontal stress. So here at Menengah, your long axis is roughly northeast southwest. And looking at some of the data I've analysed from focal mechanisms, extension within that region is also along sort of northeast southwest rather than east west, which is something that a lot of people seem to sort of loosely think is the case. Then that would align that actually the regional horizontal stresses seem to be controlling the formation of the caldera, but this fluctuates right across the rift, even just in Kenya, where the Rift Valley is overall north-south, and the regional stresses are, like I say, roughly northeast-southwest. But the further north you go into the rift, the long axis of the calderas change direction and are perpendicular to that principal horizontal stress. So it's really confusing, and I'm still not convinced. I'm still not 100% sure.
That's really interesting, actually. So the long axis of the caldera being aligned to, so it's aligned to basically the axis of the rift, or to the axis of, or to the direction of extension.
It's a direction of extension. So, and in this case, it's probably because obviously you've got that kink in the rift trend. So sort of where Menengah is, the rift trend is sort of north-northwest, north-northwest, south-southeast, but north of that it's almost north-south, and south of that it's almost north-south. And so based on that little segment, the principal horizontal stress and the long axis of the caldera are probably close to, probably oblique, slightly oblique, the principal horizontal stress and the rift margins.
Yeah, if that's where the kink in the rift is, I would expect weird stress orientations and something that's not quite in the norm for the standard rift sections. So
yeah, I mean, absolutely, it's really, I mean, it's such a complicated area, and that little kink in the rift there, as I mentioned, is believed to be controlled by the north-northwest, south-southeast asphalt lineament, which is Pan-African. It's 3.5 billion years old. It's a really deep basement structure that's still influencing what's going on at the surface. And then you've got the east-west structure coming in from Lake Victoria and meeting that triple junction there. And there's a whole host of stuff going on. It's all very, very strange. And of course, then when you take into consideration where extension is being accommodated by dike intrusions as well, and that can sometimes locally change the stress regimes as well. So it is really complicated, head-hurting complicated sometimes, I think.
Yeah, I figured.
That's why you're helping me with this paper, Dave.
That was really great, Helen. I really enjoyed that. Thank you.
Good. Anybody else?
Hello, different sort of question, but it just occurred to me, you were talking a little bit about volcanology, and obviously in general, volcanologists will focus their attention on volcanoes where there's big risk to human population from eruptions. But where you've got a volcano or caldera like this, where there's still active but not actually erupting, I imagine there's not a huge amount of volcanologist activity. But if there was more volcano, like satellite monitoring or inflation or things like that volcanologists might do for other volcanoes, would that be of benefit in terms of helping you develop a conceptual model?
Yeah, I mean, so Menengah underwent I think it was about 7.5 centimetre deflation during the 1997-2000 INSAR survey. And it doesn't appear to have inflated since. There was another survey pass done 3 years ago, I think it was, and there was no change to the edifice then, whereas other volcanic systems in Kenya had changed again after that first survey. So I guess it could help a little bit because you could sort of try and estimate how much deflation relates to magma depth and magma drainage and things like that. I guess one of the biggest problems that we've got now with respect to Menengah is the huge volumes of water that they are abstracting. Bearing in mind, so for example, if you remember the plot I had with the wells and I had that yellow circle, that well there, like I mentioned, electricity has failed but is producing heat. That well alone discharges 60 tons of fluid a day, and it discharges 365 days of the year. And then if you've got other wells discharging, it could be discharging 2, 3, 4 times more water than that. You might find you get deflation, shallow deflation, resulting from abstraction, over abstraction of water. And you also find that if you get huge amounts of abstraction of water, so the center of the caldera is fluid dominated and the outside of the caldera is steam dominated. But if you're abstracting too much water from the center of the caldera, you actually encourage the movement of steam into the center of the caldera, which then gives you these huge kickbacks on the drill string. And there was a considerable blowout in the center of the caldera about 3 years ago, I think it was. And so I think using INSAR on somewhere like Menengah now could be problematic because of the amount of water being removed from the reservoir and less is being injected back in. And I suppose to counteract all of that, work would need to be done on sort of lake balances. So looking at the lake balance of Lake Nakuru, an inflow from Lake Nakuru, an outflow of Lake Nakuru in relation to what's going on at the caldera as well, to see whether you can counteract that effect. And you know, so if recharge to the reservoir is matched by discharge from various sources, then maybe then you could use INSAR, inflation and deflation, and associate that with magmatic activity rather than the geothermal activity. But that's a lot of work, and doing a lake balance for Lake Nakuru would be really, really challenging because there's loads of rivers that drain toward Lake Nakuru, but only 2 of them drain actually into the lake. The rest of the rivers that run all year drain down faults and then are reported to recharge the lake from the subsurface. But large areas of the lake bed are also very clay rich, and so there's this impermeable barrier there as well with respect to that. So there's a lot to think about. And there would be a lot of gaps in the data, I think, because there's no flow rate data for the rivers at the moment. There's no flow rate data for the springs that are draining into the lake, and there's no real understanding of the outflow volumes from the lake to wherever it might be going, whether that is Menengah or elsewhere.
Helen, what is the re-injection ratio, if any, from the field? I mean, how much of the production is re-injected?
If I recall correctly, they re-inject about 80%, right, if I remember correctly.
But that net production is still having some impact.
Yeah, that net production. That net production. Sort of very quickly off the top of my head with the numbers that I know of, the net production, I would say, outweighs that.
Anyway, very interesting. Thanks.
Any more questions?
Thank you very much. This was great.
Not keeping you all from your wine tonight. You can all go now.
Thanks, Helen. Great presentation. Really interesting.
I've got to practice not getting tongue-tied, but then I suppose that's...
Thank you, Helen.
Hi, Jessie. Habari. Oh my gosh, I can't remember what evening is. Habari Zahazabusi, am I right?
We are doing quite fine. It's past 10 as we speak.
Hey?
Hi, it's past 10 here in Nairobi.
Yeah. I think you might be breaking up a bit, Jessie. I can't quite hear you.
Yes, he's saying it's past 10 p.m. in Nairobi.
Oh, it's past 10 p.m. Oh, asante, Jesse. Pole.
Are there any other questions for Helen?
I was actually wondering, have you tried to compare with geophysical data like MT or gravity? You said there were some exploration data there. You tried to compare the results with the theory of the ring caldera?
So the amount of geophysical data they've done versus what they've released is quite limited. And this is sort of, I mean, we see this everywhere, any kind of subsurface exploration. We see that there's sort of a lot of secrecy around releasing that data. And so I think the data they've released is selective and quite informative. So there's only, like I mentioned, they did one microseismicity cross-section, one magnetotelluric, and 4 gravity surveys. But it doesn't mean to say that there isn't more, it's just what's been made available through publications. And both gravity surveys and the magnetotellurics pick up something by the changes in signal coming back to the surface. So the magnetotellurics, for example, has a, I'm trying to remember which way around it is now, I think it's a low resistivity in almost, so there's a couple of vertical sections of low resistivity, and you can clearly see the first collapse, and there are hints of what could be the second collapse on a much smaller scale. The gravity concentrated more on intrusions and where sort of the shallower intrusions were and what depths they were going to, and doesn't really go into the details and wasn't really looking for the internal structures of the caldera. So it's only really the one MT data that shows that. And actually, funnily enough, that MT data also shows a magma body that's consistent with a funnel collapse rather than a piecemeal collapse, even though they believe Menengah is a piecemeal collapse. So that's something that also needs exploring. When I'm talking about know your caldera, there's certainly some contradictions on what they're saying and what some of the data is telling us as well. So, yeah.
Yeah, thanks. It was very interesting.
Anybody else? That might be it, Claire.
Yeah, I was going to say that was great and some really good questions at the end. I think I was doing some training down in Olkaria last year, but I've never headed up to Menengah, so it's good to gain a bit more understanding about it, and particularly about the structure, because we did a paper a couple of years ago with the team at GDC, and we modelled the MT data in Leapfrog as well as the temperature data from the wells, but we didn't get the opportunity as part of that to look at the structure in more detail. So it's good to have that little bit more of pieces added into it.
Definitely needs exploring, and not just for Menengah. I mean, Menengah is well on its way for development, and there have been successful wells. There's been a considerable amount of failed wells as well, and those failed wells don't sit within that proposed structure or target that proposed structure. Some of them are too far south for that structure, and some of them are in the northeast corner. But going forward for other caldera developments, wherever that might be, it's really important to understand what your, the structures, the collapse mechanisms of your caldera and where those structures might be, because they're likely going to be those permeability zones that you really need to be targeting for fluid flow of whatever that might be. And using the CO2 flux as well. I mean, I did mention that certainly in a volcanic setting, how CO2 degassing is the fastest after water vapor. And And CO2 is definitely, you know, the flux measurements is no replacement for other stuff, but to use it alongside, I mean, the advantage of flux data collection is, comparatively speaking, the equipment is cheap. So that kit's about £5,000. And you don't need to haul around heavy replacement batteries with you, and it'll last a good 8 or 9 hours of a survey being constantly switched on. And the data that you get, it produces data in grams per meter square per hour, and to convert that today, you just times the value by 24, and that's your raw data for you to then start processing in ArcGIS on, you know, geostatistical analysis for various aspects. There's very little that you need to do with that data. Whereas if you're doing geophysics and only geophysics, for example, it's much more time consuming, it's much more, you know, the equipment is much more bulky. I mean, that CO2 flux survey that I did, it was 124 sites, and I did it in a total of 5 weeks. And some of that was driving, about over half of that was on foot. And the spacing of sites was sort of 40 to 50 meters in most cases, with some of them being a bit bigger. But there are limitations with the flux. So, for example, you can't use it in areas where there's fresh lava because you get interference from atmospheric CO2. You can't get the collar deep enough into the ground, into the soil, because if it's fresh lava, it's not eroded. And so you need to apply other methods, and whether that's degassing for radon or helium, and of course geophysics. But you can use the technique, the CO2 flux technique, like I say, to identify permeability zones or potential permeability zones that might then further guide where you locate some of your initial wells for exploration in the subsurface.